Ni hao ma, Math Ninja here. So this week, Paul, you had a question on extreme problems of the maximum problem, Shifrin page 207, number 2. Okay, so you had the right idea, but you have to encode the boundaries somehow. So you had the right idea on your solution, finding the critical points. So, okay, if this was if we were dealing with a real number line, and a continuous differentiable function on the real number line, we'll have to check two things. Where the critical points equal 0, and the boundary points, right? But when you're working in R3, the boundary points may be more, may be bigger. So, so you have to check those as well. And you have to parameterize the boundary. So you have to plug in all points that describe in one case, the circumference, the outer boundary points of a circle. Or in the previous example, example number 4, you talk about a rectangle. You have to parameterize each of the lines and consider the max where it occurs when it's on that line. We plugged in the values, what the line has to look like. And to solve that, we use single variable calculus. But question number 2 is even simpler than that. So your solution x, y, and z being the function. So here's the problem though. Your function is not just x times y times z. You have x because of the hyperplane. X is a function of y and z. So the thing is, you want the volume, right? And you have a point at the origin. You have the edges parallel to the axes. So all we have to do is find the maximum of the box that you can make when it's on the hyperplane, where the y and z is determined, where the x is determined by the y and z. So let's talk about that, because we know one corner has to be on that hyperplane, but we don't know where. We have to optimize that. Okay. So the question is, a rectangular box. No, red is always good. Red is the color of desire. Red is box. A rectangular box. And this is page 207, number 2 of Shifrin, Introduction to Multivariable Calculus. A rectangular box has, let's see, edges parallel to the coordinate axis, parallel to the coordinate axis, and the next part is here. And one corner at origin and the other corner on the plane x plus 2y plus 3z. X plus 2y plus 3z equals 6. Is that right? Okay. What is the max volume? Okay. Well, so in your solution, you wrote f of x, y, z. Of f of x, y, z equals x times y times z. You just found the max of that, but you just found you computed the Jacobian of that. But dude, that's not it, because you have to talk about this specific box. So how do we talk about this specific box? Okay, this is bad color. Okay, let's draw it. Always good to draw the picture, but remember, a picture I'm not the proof. So to draw the picture, we're in 3 dimensions, right? X, Y, Z. So we have one corner here, right? parallel to the edges. And it has another corner, opposite corner. It's so hard to do. What can we do with that? Okay. Logic does not have much of geometry drawing, so let's say so maybe this has to be more. One corner origin. Okay, this is good. So one corner is at the origin. Well, maybe I should make the other way. It's okay. Have this negative sign. Okay. So the one corner here, and this corner has to be on the hyperplane. Sorry. X plus 2y plus 3z equals 6. So what notice that because we're starting from the origin, because one corner is at the origin, it's enough to find out, to maximize the hyperplane where it is. Remember, since we're starting at the origin, all we do is find the max x to this hyperplane, max y to this hyperplane, max z to this hyperplane. Other opposite end of the corner. So, but here's the thing. So now we have to determine the x. So we just have to determine the x, y, z on the hyperplane. Because remember, the other end starts at 0. 0, 0, 0, right? So it's just enough to find out the maximum value on the hyperplane. Because that's so the function should optimize f, x, y, z, right? Volume is equal to x, y, z. But this x is determined, the distance from this here to here is actually going to be x, it's going to be determined by x plus 2y plus 3z equals 6. So what should x be? So y, this is a plane, y and z can be anything in the world. But when you choose what y and z are, it determines what x is. Why? Because x plus 2y plus 3z equals 6 is equivalent to saying 6 minus x minus 6 minus 2y, right, minus 2y minus 3z equals x. Just move to the right. So this guy, the function you're optimizing is not x, y, z. It's actually plug in for x. So it's going to be 6 minus 2y minus 3z times yz equals 6yz minus 2y squared z minus 3yz squared. Let's check. Yep. Z, yep. 3z squared. Yeah. So now we just have to optimize this function. Remember, y and z can be anything, but x is determined by y and z. So now let's continue. How do we go from here? What can we do? Continuous functions. What can we do? Find the critical points. But first we have to find critical points. So first find the Jacobian. Okay. Derivative of f with respect to x, y, z. Remember, this is r3 to r1, so we take the first derivative with respect to x at this guy, and that equals 0. Take derivative with respect to y, and this equals, you know, I should really do these problems in advance. It would make it so much easier. So, 6. Okay. But hopefully, some beautiful math girl would see this and say, wow, this guy is smart. Anyways, 6